Okay, don't be scared for we have too many formulas, because in the real life we using no all of them. You're using the most important or the most useful. Now, suppose implicit. It's another possibility. En implicit, bueno, the normal vector is easy. The normal vector is the gradient of capital F divided by magnitude of this. This is the formula for the normal vector. And this is what is the formula for the ds. ds is a gradient in 3 dimensions. This is vector, right? Vector, 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 divided by magnitude of this, but multiplication by any unit vector, any orthonormal unit vector. Okay, remember the orthonormal unit vector are the famous K, J, and I. 0, is a vector. 0, 1, 0, 1, 0, or 1, 0, 0. And it's a P, multiplication by P. And depending the unit vector you select, you have here dA, because this is a transformation from the surface integral to double integral. Suppose it's a vector, guys. Because that part is vector, that part is scalar, and this part is scalar. Suppose a scenario, more popular scenario, que es ds vector is the computation, the gradient of the implicit function divided by the gradient dot product K. Entonces we have dA is transformed like a dx dy, because K is a vector que is perpendicular to this plane. Likewise, you have J here, then Sj is perpendicular to the plane xz, this is xz, and I is perpendicular to the plane yz. And you have 3 equations similar to this. Do you understand this? Do you understand the idea? There are many possibilities, but this is not bad. This is good. Suppose, no, professor, no. I want parametrization. Okay, no problem. I want explicit. The majority of the book, to simplify the thing, explain basic explicit only. And the different version, but omits parametrization, because considering the student don't understand very well the parametrization and never touch implicit. Okay, I respect that. Okay, because I propose you bring 3 examples, one of them. But no big deal, super easy, because I want to explain another topic as the last one. Again, the story, we start review. Okay, I can erase the board or not yet? Yes or no? Okay, let me start for elementary. Super easy example. Suppose example 1. Okay, we have a vector field, always is given. It's obvious, no? And the vector field is weird. It's cosine xy. Remember, vector field is a vector contain 3 components in 3 dimensions, PQR, exponential, and phi. Wow, it's a constant. This is P, this is Q, and this is R. Okay, thus I want to find the flux integral of this vector field. And the surface is expressed mathematically or graphically as the uni square. What is that? Uni square in the xy plane, uni square, but only in the first octave, something like that. Okay, our surface, a uni square, is a 1, okay, and this is, okay, this is 1, 0, 0. This is 0, 1, 0. And this is the point, que es 1, 1, 0. Because we have no z value. So this is my surface. Okay, day one, okay, you compute the surface integral. Okay? This is obvious. Look at the figure. No mathematics. Okay, the unit vector, the normal unit vector, is k. K is a vector like that. K. And k, you know, que es 0, 0, 1. And now perform the dot product in between this vector que es PQR and 0, 0, 1. Es obvio que the dot product in between this and unit vector. Remember, we have two possibilities to analyze this. The possibility of this or the possibility F vector field dot product unit vector, and you consider this like a constant, ¿no? Entonces, cuando you perform, es obvio que 0 times cosine es 0 y 0 times exponential es 0. Entonces, 1 times 5 es 5. It's only 5. I did intentional, this elementary example. Entonces, no necessary too much mathematics in this case. So, no, sometimes no, sometimes yes. But this case is a flat surface. And according to the position, I see that the normal vector is k, but so you take advantage of this. Okay. Now, my surface integral is reduced to the double integral, and the integral function is just phi, and here, and this is dA. Okay, by the way, this dA is dx dy. Well, this is not necessary calculus, because phi is a constant, go outside. And the double integral of the area is the area for this square, que obviously the area is 1. The answer is 5. Boom, phi is a flux. Okay, so this is represent, remember the interpretation for the flux. The flux is the amount of vector field crossing this surface. F5. Phi, I don't know. So you need to understand physical interpretation. So you need to understand what is the vector field, what is the nature, what is the physical interpretation of this vector field. Is a force, is a velocity, is acceleration. This is another thing, okay, it's beyond mathematics, okay? Our problem now is we'll be able to compute the flux integral. I don't know, I don't care too much what is the vector field, what is the physical interpretation of this vector field, and I don't know exactly, or I don't care bueno, sí, I care, o sea, what is the surface que I need to compute the flux, okay? Entonces let's do it. This is what super easy, not necessary formulas to compute this problem. I have another, a little bit more interesting. Example 2. in which you have vector field again. 3y x6. I have surface. Sometimes the surface defined mathematically, or no, or sometimes it's defined geometrically. So this is z is equal x plus 3y squared minus xy. This surface is very, very weird. No, it's the classical quadric surface, you know, paraboloid, ellipsoid. No, this is crazy. Okay, and define specifically in the interval between 0 and 1 in x, and y, and between 0 and 1 in y. Entonces, this information suggests a little bit, okay, we are working in explicit because C is isolated. Entonces, we're using the famous formula que the double integral in the surface S f dot ds. We can compute it with that formula, no? Is you convert to the double integral, and you're using the formula que es minus p partial derivative x with respect to the x minus q partial derivative f with respect to y plus r. And this is the dx dy, I don't know, or dy dx, depending on the order in que I decide. En general es dA, pero no involve C. Es dx dy porque I projecting. So the explicit is considered que the x and y are independent variable and C is dependent. Okay, so the only thing you should do is compute the partial derivative of the surface fx and fy. Now fx is differentiate this with respect to x is 1 minus y, because this is 0 and this is 1, but it stay y alive. I differentiate, remember this is equivalent to say fx comma 1. I am doing the partial derivative with respect to x. And likewise, partial derivative with respect to y is 6y minus x. Makes sense, right? And the rest is easy. The rest is plugging in everything together. Put everything together. Who is P? This is P. This is Q. This is R. So now, double integral. After I set out the limit, you put here 3y or minus, no? Minus. We have minus here. This minus, look. P is 3y minus 3y multiplication by the derivative is 1 minus y. Minus. We continue here minus q is x. Multiplication by this partial derivative is 6y minus x plus r is just 6. To say integrate the y dx, because the region R is this actually. The region R, so you want to see graphically, is something like that. 0 to 1, 0 to 1. This is the region R. Therefore, the order of the integration may be, we are doing like that. So you integration first, with respect to dy, is from 0 to 1, from 0 to 1. Guys, the rest is super easy. The rest is algebra. You distribute it, combine like term, and compute double integral. And you know that. The answer is 13 over 2. Okay, so we're using this formula when we have explicit form. And how do you know que es explicit form? Because C es isolated, o X es isolated, o Y es isolated. Cool? Do you understand this problem? Any question? Any formulas? No, you need to understand the logic of the problem, no? But it's basically it's the formula. Let's do another problem in which I using example 3, no? So I did the first example was without formulas, and the second example was explicit, and the third example is like a implicit. Suppose que es vector field. And by the way, in the test you are doing it in the way you consider better. Suppose the vector field is given. This is PQR, P is 0, Q is Y, R is -0. And the surface is, well, Y equal X squared plus C squared. This is a paraboloid. But this paraboloid is alone, paraboloide, pero along Y, que es the verb que es no square. And Y is in between 0 and 1. Okay, let me try to understand my surface. Always is useful. Try to do your best doing the sketch to understand surface. In this case, paraboloid. This paraboloid look like that. And Y vary from 0, que es this, to 1. Suppose this one. Entonces, basically, my surface is this. Okay. This is my surface. So the surface is formed by the paraboloid walk in between Y0 and Y1. And the question is, Professor, and what about that surface? No, this surface not included in the problem. And when I say I want to include in the problem, well, you can. You can, but you are doing another surface integral. Okay? So you are doing any surface integral depending the faces that you consider in your problem have in our surface. So not necessarily as a simple surface, is compound surface, is a combination of several surfaces. And you see that now the problem is to compute the surface integral in any surface. But in this case, no. To simplify the thing, no. I consider only the paraboloid face as the important. The other, no, I don't care. The other is hollow, maybe. Okay, so now the capital F, X, Y, Z. Okay, when you talk about F or capital F, it's about surface. So I ignore. Don't confuse in this F. This is vector. This is no vector. Vector, no. It's just surface. Is X squared plus C squared minus Y equal to 0. Remember, equal to 0 on the right hand side because I consider it implicit. And to compute the gradient of this is partial derivative with respect to X, que es 2X, comma, partial derivative with respect to Y, que es -1, and partial derivative with respect to C, que es 2C. Okay, entonces suppose que I make decision to apply that formula. This vector is this gradient divided by this gradient multiplication by P unit vector K select. Okay, obviously in this problem the most convenient unit vector we're using is J. It's J. So since it's J, here we have dx dc. Okay, because you know the paraboloid is along the y-axis, so I'm using J. J, que you know J is in that direction. Okay. So now it's easy. Is this vector, this 2x, comma, -1, comma, 2c, divided by the dot product. Remember J is 0, 1, 0. And you multiply this times this. It's obvious que the only guy que stay alive is -1. Because 0 times this is 0, 1 times -1 is -1, and 0 times 0 is 0. But you find the magnitudes at the actual value of the basic is 1. The ds is perfect coincident in this case with the gradient. Cool. See, it's like that. 2x, comma, -1, comma 2c. My flux surface integral vectorial should be equal the double integral in the region R. Okay, I want to illustrate who is the region R. Okay, is the vector field. I copy my vector field, dot product. I copy my ds vector, okay, is 2x, comma, -1, comma, 2z, dA. And dA obviously, according to this idea, is dx dz or dz dx. I don't know exactly what is the most convenient way to solve it. Okay, multiplication, dot product. Dot product is 0 times something is 0. This time this is -y. It's a double integral in the region R. And the integrand function is -y, que es this multiplication, this and this. And this case minus 2c squared dA. Okay, cool. Okay. Now ready. What is my region R? Well, my region R. Well, no. Okay, I need to fix something. Remember, the variable que participate in the game is C and X, and we have Y here. And you need to do something in order to eliminate this Y. But it's easy, because I know que Y is equal X squared plus C squared. Okay, so now my problem is double integral in the region R. Entonces es minus X squared minus C squared minus 2C squared. Do you see that? Yeah. The only thing I did was substitution is here. And this minus, of course, affect everything. Therefore, my double integral is minus x squared minus 3c squared. Entonces, I suppose que I integrate dx dy or dc dy. But in this case, the projection of the region R, okay, I don't determine who is the region R, but the region R is the projection, our surface, onto onto the ZX plane. Entonces now I suppose que at y equal 1 here, this projection is a circle, and this circle, let me try to do the view in 2 dimensions. This is the view in 3 dimensions. The view in 2 dimensions is the plane XC. It's a circle with a radius 1. This is 1, this is 1, this is negative 1. This is the projection. The projection, our surface onto the XC plane. Exactly the same we are doing before. So now I propose you convert to polar. It's obvious, no? The circle is polar. You ending in polar. You ending in polar, well, you any variable you put in polar. I know very well that x is okay. You put the negative outside. I put the negative outside. Look, I put the negative. Too many negative. I put a negative outside. I copy now x squared plus 3c squared dA. Now it's a moment to convert to polar. This is, you know que, okay, the equation in polar is x is equal r cosine theta, and normally y is r sine, but in this case, no, it's not y, it's z, because we have applied polar in the XC plane, not in the traditional, the C. The traditional that we apply always is in the XY plane, but in this case, XC plane. It's the same. Entonces es R squared cosine squared theta plus 3 times R squared sine squared theta. The Jacobian R dr d theta. Entonces en our region R, this is the region R, this is the region R, is from the radius go from 0 to 1, and the theta go from 0 to 5. Okay. No big deal. It's acceptable. The answer is minus pi. Okay, as always, I skip the tedious calculus 1, algebra and arithmetic, because I want to focus in the calculus 3 part. Do you understand the mechanism? Do you understand the algorithm? You need to concentrate a little bit to understand the problem, no? What is the surface? What method you using? C implicit, C explicit. In this case, I'm using implicit. And ending in one double integral. In this case, was convenient projecting onto the XC plane. Okay, cool. And finally, we ending in polar. It's logical because the region R is the circle, no? Okay. One more example of the flux integral in 3 dimensions. And this example I want to do by parametrization. So this is example 4, no? 1, 2, 3, 4. This is 4, no? It's 4. Yeah, it's 4, no? It's 4. Suppose the vector field, easy, is 0, 0, x squared plus y squared. Wow, what the hell? So this vector field, in my opinion, it looks like that. Right? Because no component in x, no component in y. Okay, of course, we are talking about 3 dimensional. and only have component sig, and by the way, it's positive because it's the sum of two squares, so it's outward. It's the vector field. P is 0, Q is 0, and R is x squared plus y squared. This is the vector field que is given in the problem, no? And the surface, let me try to express it, is a disk. Let me try to do graphical. The surface is a disk. Remember, this is not circle, because circle is the circumference, the border, the boundary. However, this is so not solely a flat, but is inside. But this is something like that. This the center here. This is the disk. What is the parameter of C of the disk? The center is located at the point 0, 0, -4. And the radius is 6. This is my disk, this is my surface. Okay, I want to put or compute and this flux integral. So basically the thing I try to do is compute the flux. It's the amount of vector field, this vector field passing through, crossing to this surface. Entonces the flux depending of the three things. Depending the vector field. Depending the surface. Because you suppose that you have big surface, we have more flux, no? Because the amount of vector field crossing. And depending the orientation. Or basically the angle in between. Because if it's perpendicular, no flux, you know. So one possibility for solving this is parametrization of the disk. Let me try to do my best. The parametrization of the disk is super easy because the vector value function can represent the parametrization depending of two things, depending the radius and depending the angle. Why radius? Because this is belong to this, belong to this. No is equal to the parametrization of the circle, depending only one parameter because it's a curve. No, this is surface. Depending two parameters. And R, it's obvious R vary from 0 to 6. And theta vary from 0 to pi to form a disk. And it's relatively easy, the parametrization, because you have R cosine theta. R is variable, no constant. See, R is constant, que es 6. Entonces es a circle. No circle, es a disk. Comma R sine theta, makes sense, right? And what about C component? C component is -4. C component is -4. And when you put this in the algebra, if you want to see, you put surface command. You copy this equation. In algebra using B and U. B sine U, comma -4. No dependent on nothing, is constant. And U vary from 0 to pi. And B vary from 0 to 6. And when you press enter, you see, wow, this super cool. So now, if I make a decision to the parametrization part, I need to compute the partial derivative of the vector value function with respect to theta. You differentiate with respect to theta, component by component, is minus R sine theta, comma R cosine theta, comma 0. Because derivative constant is 0, no? The partial derivative of the vector value function with respect to r is cosine theta, because you consider que theta is constant, no? Okay. You consider que theta is constant. Derivative r with respect to r is 1, comma, sine theta, comma, 0 again. Because derivative constant is 0. And when you perform the cross product of this, using the idea that always we use ijk, you copy this component minus r sine theta, r cosine theta, and 0, cosine theta, sine theta, and 0. The answer is 0, 0, r. Unbelievable. No theta. It's good. Okay, now our vector field is this. Remember, right? Our vector field is this. Our vector field is expressed like a function of the new variable, que is not xy anymore. No, it's r and theta. Is our vector field is the vector 0, 0, r squared. Makes sense, right? And the ds is this vector, que is 0, 0, r. And of course, dr d theta. And now you are doing the famous dot product, because my surface integral is surface integral of the 0, 0, r squared dot product 0, 0, r dr d theta. This is so far is surface integral. But when you perform the dot product, ya is no vector anymore. It's r cubed, no? 0 times 0 plus 0 times 0 plus r squared times r cubed dr d theta. And it's now the double integral in the region r. Now, who is the region r? The region r is obvious que es the projection. Bueno, the region r, no projection, es parametrization. Entonces es en a new plane, abstract plane, theta r, que es this condition, is from 0 to pi and from 0 to 6. This is my region r. It's my region r. Entonces now set up this double integral is super easy, because it's only r cubed dr d theta, r vary from 0 to 6, and this, and theta vary from 0 to pi, and this. Wow. And you compare the answer is 648.5. And the thing is, at least for me, a little bit confusing is, well, professor, there are no Jacobian here. No Jacobian, because actually we don't do chain of variable, because when I did the parametrization, of course, the best way to do parametrization, my region of the integration is rectangular. Okay, so I actually like a parametrization. I want to discuss it, but no now in detail this idea. Parametrization is family of the substitution. But the problem, professor, is que in substitution you need to put the Jacobian. In parametrization, no. Okay? I want to explain in your moment. not today. I suppose que after the review, this idea. This is extra problem to K1. Okay, guys. So now the last part of the vector calculus is we study two super important theorems. The first one is Stoke theorem. Stoke theorem. Okay, Stoke theorem. Stoke is the last name for the famous mathematician. Okay, what is the idea for Stoke? Stoke say, let S be a piecewise smooth surface orientable. I want to explain it what means piecewise smooth and orientable. I explained no the last time, but I want to explain it in R3, three-dimensional space with boundary. Boundary is a new idea. I can introduce this theorem. Boundary C can normally, I don't know why, call it like that. Delta S. I want to explain the sketch now. In positive direction. Positive direction. I want to explain what is positive direction. There are too many concepts inside this. And of course, let a vector field with three components, PQR. And PQR are continuous. Continuous and differentiable. So continue the function PQR, and also the partial derivatives are also continuous. Okay. Then, is to say, then the conclusion, then the conclusion of the Stoke say, the line integral circulation and the closed curve C of the vector field, the dr, is a classical circulation integral is equal to the surface integral of the curve of the vector field that ds. This look like similar to the Green theorem, but in 3 dimensions. Green theorem is in 2 dimensions. Stoke is a similar idea, but in 3 dimensions. Okay, but let me explain quickly. What means piecewise smooth surface? Bueno, suppose que the classical surface is smooth, paraboloid, but I want to complicate, for example, your life. Suppose a box. So a box is formed by different surfaces. The phase 1, the phase 2, the phase 3. Entonces, a piece smooth means que one piece is smooth. It's smooth in that part, and it's smooth in that part, and it's smooth in that part. This is piece smooth surface. Okay, it's differentiable in different interval. Orientable, do you know the idea that we discussed last time? Okay, we have surfaces orientable and non-orientable. Dependency, the surface have two faces or no. Entonces, si es orientable, es because this is the classical surface, and we define the normal vector in the direction that you prefer. So you want to compute the flux, okay, leaving the surface or get in surface. Okay. Now, in this case, okay, I want to do now, we have two guys and the problem. We have the surface, suppose like that. This is the surface, smooth, nice. And you have the boundary, and the boundary is a curve. So we have a curve C, look, participate in the theorem, and the surface S, participate in the theorem. Okay, entonces the formula of the equation of the Stoke theorem is good, is compatible if suppose que you walking, suppose que this is you. And you walking around the curve and the direction gets indicated here. And your head point in the direction of the unit vector. When you see one of professor, the direction of the unit vector, maybe it's like that, like that. You can rotate. So you're walking, but your head try to point to the unit vector. Maybe you incline a little bit your head. And your left hand, left, not right, left, point in the direction of the curve, inside the curve. So if you're walking around the boundary, okay, the boundary is the curve C, with your head in the direction of the way you're choosing the orientation of the surface, que basically is the normal vector that you need, and your left arm is over the surface S, so this is positive orientation. This is the idea behind the theorem, positive direction, so this is positive. Suppose que es opposite, que es not the left, it's the right. Well, entonces the formula is the same, but you put a negative here, right? That's it, it's the only difference. It's the only difference. And the beauty of the Stoke is que stay connection in between two kinds of integral. We have in the left hand side, we have line integral in the closed curve. In the right hand side, we have surface integral. Entonces, depende of the problem, we can solve it using line integral or using the surface integral. Es obvio que si our surface is complicated, or our maybe it's much better doing by line integral around the boundary, because surface too long, because we have different faces. I don't know, depending on the problem. So now the other important idea I want, theoretical idea I want to emphasize, okay, it doesn't matter what surface you're using. Suppose three scenarios. Suppose que this is my curve, C. Remember, C is del S, que es the boundary. That's a new concept I want to introduce. You talking about boundary. Okay. Now, suppose que the surface like that, similar, no? To this. This is the unit vector, nice, no problem. But suppose que the surface like that. And this is my unit vector, I suppose, no? Or in another direction, no? And suppose this is my surface. And this is my surface. And now this is my surface, totally flat. Surface. And the answer, can you compute using any surface, is the same. Wow, amazing. This is called a surface independent. Of the curve. Okay. Entonces, obvio, si the problem do not depend on the surface que you define, entonces I'm using the easy surface. What is the easy surface? This is the easy surface, super flat. Entonces it's easy surface. Okay, easier. surface. It's surface independent problem. Okay. 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 Let me try one problem of the Stoke. O sea, Stoke, si I explain in few words, is one theorem similar to the green, que allow us the connection between two integral, one integral que is a line integral and the closed curve, and the surface integral using the curve. Rest, in my opinion, the three-dimensional version of the green theorem, the more general. Okay, so now example. Only one example I bring for the Stoke. Suppose example one of the Stoke is the only example that we have. I promise in the review packet we are doing more, no? We have a vector field. This vector field is minus y, comma x, comma 0, PQR. And the surface S is again no, this is a sphere, x squared plus y squared plus c squared equal 4, and c is greater than or equal to 0. So actually it's hemisphere, so the top part. See, I try to do, okay, it's a hemisphere. You know, my whiteboard try to fix it to some time now. Okay, this is part, this is another part, and this is sphere. And this is sphere, the radius is 2. So this is my surface. Hemisphere. This is S. And this is the C, que es the curve. Yeah, I suppose always to simplify the thing, the positive orientation, no? Positive direction. Positive direction. Okay, now so now I want to compute the problem using two pieces of verification Stoke. I want to compute using the, remember, Stoke say integral and the closed curve C of this vector field that dr is equal the surface integral, pero the integrand function is the curve. Double this. Okay, and so I make a decision to do it that way. So you compute the curve, or you compute the vector field, or you compute the normal vector. Okay, you compute the curve. Let's do it. The curve is the curve of the vector field F. Be familiar with this notation. Nabla cross product F. Who is Nabla? This is IJK. Nabla symbolic way, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. And en F es the component PQR, que es minus y, x and 0. Okay, as always, I try to skip that part. And the answer is a vector, que es 0, 0, 2. Okay, cool. I know. So what about ds? Well, ds, I want to using another idea. This is the curve, but I know that the normal vector in the sphere is equal x over a, you remember that, comma y over a, comma c over a. It's totally radial, normal vector is radial. And who is a? A is 2, gets the radial. Actually, the normal vector is x over 2, y over 2, and c over 2. This is a formula for the normal vector in the sphere. Because I know that you ending the surface integral and the dot product, this vector, que is a curve, dot product, the normal vector. Because remember, this ds is normal vector ds. So normal vector is x over 2, comma y over 2, comma c over 2. And this is ds. Okay? And you perform the dot product. And the dot product is multiplication. Multiplication, there's a multiplication 0 times something, 0. 0 times something, 0. And this time this is 2. It's a double integral in the region R of the C, because these 2 and these 2 is cancelled. ds. And this is the complicated here, because I want to parametrization the surface. And the best way to parametrization a sphere surface is using a spherical coordinate. So I suppose vector value function that depending on the two famous variables que we use in a spherical, que es phi and theta. And the radius 2, que is constant, because it's on the sphere. Entonces, 2 sine phi cosine theta, comma 2 sine phi sine theta, comma 2 cosine phi. Let me recall quickly the formulas in spherical. In spherical is x is equal rho sine phi cosine theta, y is equal rho sine phi sine theta, and c is equal rho cosine phi. But we are working with the sphere and the rho is 2. So the only thing I replace rho equal to 2 to 2, I obtain vector value function and end the story. So now the tedious idea, it always happens. You need to differentiate this vector value function with respect to R, cross product, with respect to theta, cross product. Guys, I want to avoid this idea because it's too long. And find the magnitude of this. And magically happen that the answer is 4 sine phi. And it's expecting, because you remember the Jacobian in spherical, the Jacobian is rho square sine phi, d rho, d phi, d theta. But which rho is 2 and 2 squared 4. Okay, and we have no d rho. Okay, so now my integral is reduced like that. Now it's double integral. I forgot to say important thing. Okay, phi is in between 0 and pi over 2 because it's hemisphere, no pi, and theta is in between 0 to pi. And this is important because this is our domain ending at the region R, theta phi is like that, 2 pi and pi over 2. This is my region R. Okay, we ending the double integral. Okay, entonces C es C. Es C, pero C es, look here, C, this is C. C, Y, and X, no? Entonces C es 2 cosine phi, and ds is 4 sine phi. Don't forget the phi, the theta, no? So 2 times 4 is 8. Cool. And the limit of our double integral is from 0 to pi over 2. Suppose que yo integrate first with respect to phi, and 0 to pi when you integrate with respect to theta. And the answer is 8 pi. Look like horrible, right? Too long, complicated. Entonces now it's no super hard, but it's long. So when it's long, everyone make a mistake. It's obvious, right? Okay. Entonces now I want to solve the same problem, pero using no the surface integral, que es the right hand side. No, using the line integral, que es the left hand side. Entonces in this case, I want to simplify the thing, because my curve is on the xy plane. So this integral, close integral, this is dot product and the closed curve. I can working like a pdx plus q dy. Exactly the same we are doing in 2 dimensions, because actually my boundary, my curve is 2-dimensional. And who is P and who is Q? Well, PQ is a vector field. And what is my parametrization of this? Well, my parametrization of the curve, look, this is a 2D picture. XY. This is a circle. Circle with the radius 2. And the parameterization, so I define vector value function, but in this case is vector value function only one variable, not two variables like that. This is surface, this is a curve. Is 2 cosine t, comma 2 sine t, comma 0, because we have in the curve lie in the xy plane when the c is 0. Okay. Now es obvio que x es 2 cosine t. Es obvio que y es 2 sine t. Es obvio que z es 0. Now the differential is easy. Is dx es the derivative of this, que es minus 2 sine t dt. And dy is derivative sine cosine 2 cosine t dt. Plugging in, you convert this in one elementary single integral. I forgot to specification the t domain, que es in between 0 to pi. The integration is from 0 to pi. And plugging in p. Who is p? Well, p is 2 cosine. This is pqr. This is p, and this is q, and this is r. No, p. Sorry. Ese no es pqr. Ese no es vector field. Hello. Okay. Es negative y. P es negative y. Es negative y. Pero negative y es negative 2 sine t. En parameterization, ¿no? Multiplication by dx, que dx es minus 2 sine t again, dt. Plus, this plus, q is x en our vector field, look. Entonces q es 2 cosine t multiplication by dy, que dy es tu cosine theta. Boom. The rest is, you know, in this case, multiplication, factor out 4 because 2 times 2 is 4, sine squared per cosine squared 1. Evaluate is super easy, is 8 pi. Same answer. The thing I try to illustrate is there are two different ways to compute that. So the Stoke theorem states the relationship between one line integral circulation, of course, around the closed curve to another surface integral in which the integrand function is the curve of the vector field. Okay? Okay? In the time that we have, okay, 15 minutes, I will try to explain the last theorem. Okay, is the divergence theorem. Okay. Divergence theorem is, suppose that again we have a surface S, be a closed piece Y. You know what is piece Y? Piece Y is smooth surface, which is the boundary, so the surface is the boundary of T, and T is a solid with N pointing outward. And suppose that we have also vector field PQR. And PQR, again, they are continuous function and also is continuous is partial derivative. So now the formula, then the divergence theorem states the connection in between one surface integral and the closed curve. So now the closed is a surface integral actually this is a flux. Que flux que crossing one closed surface, no? Is equal the triple integral, wow, in the volume T of the divergence of the vector field dV. Wow, divergence theorem state the connection in between surface integral and the closed surface and the solid. So what's the idea? The idea is we have, look, suppose we have a surface. This is S. However, this is suppose you have vector field, no? Bam, bam, bam. Vector field. I want to find the flux que live in the surface, or depende, no? Depende the orientation que you define. But I change my problem to the triple integral in the volume T, or in the solid T, no volume, solid T, and the integrand function is divergence. Entonces, I recall, divergence, so you have vector field, PQR, the divergence of this vector field is computed easy. It's partial derivative P with respect to X, plus partial derivative Q with respect to Y, plus partial derivative R with respect to Z. It's super easy. It's super easy. It's super easy. Okay, so let's do quickly one example in the story. Yeah, this example. Suppose, so in what application we can use in this? We're using, for example, so you have example 2, no? Example 2 of the park, example 1 was the Stoke, example 2 is the Divergence. Suppose that you have one surface, closed surface, formed by, you know, a cubic, unit cubic, and the first octet. Okay, 1, 1, 1, 1, like that, no? Unit cubic. This is my surface. This surface is this surface. And one vector field is given, no? And the problem, no? And one vector field is given. The vector field is given is 3x, comma, xy, comma, 2xc. Entonces my problem is compute the flux. So the amount of this vector field crossing the surface, but the surface is complicated because surface have 6 faces. Suppose this is x1, x2, x3, and the opposite, no? And the bottom, the right, and the left. So you compute this surface integral and the closed compound surface, you need to compute surface S1 plus double integral, surface integral, x2, and so on. Bam, 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 to x6. 2 degrees. However, remember, no, wait. Much better, instead of doing this way, I am using this way. Okay. Therefore, the first thing you should do is compute the divergence. The divergence of this vector field. This is the formula. You differentiate component by component the vector field. Entonces now es 3 partial derivative P, this is PQR. Partial derivative P with respect to x3, cool. Plus partial derivative Q with respect to y is x. Plus partial derivative R with respect to z is 2x. Okay, and this is a scalar function. So it's 3 plus 3x. This is my divergence. Yeah, I change my problem. In triple integral. Chun. The integrand function is 3 plus 3x. And now dv. Okay, and the solid t. Okay, the solid t is the solid inside this. Cool. Now it's super easy because in Cartesian, not necessary transformation for any sophisticated coordinate. No. Cartesian because suppose that I make a decision to do in this order 3 plus 3x dx, dy, dc, and x vary from 0 to 1, y vary to 0 to 1, because intentionally I put an easy example. Well, easy no, because in that way it's horrible, using face by face. However, in the solid no, it's easy. Okay, entonces I compute that. Triple integral, you know how. It's iterative. Compute the x part after, compute the y part, and so on. Or you can separate. In this case, you can separate because it's separable. This is depending only the x. To say basically they only depend on y. So you separate like that. Look, 3 integral. This integral is 3x. 3 plus 3x. Sorry. 3 plus 3x dx from 0 to 1, dy alone from 0 to 1, and this is from 0 to 1, dc. It's obvious that this is 1. And this is no. This is, I compute that, the answer is 9/2. And this is the flux. of this surface crossing by this vector field. Okay? Okay, so the divergence Stoke. So we have time to do at least one problem of the review, or no? Yeah, I suppose yes, no? Or no? But you are tired. Guy, are you too quiet today? You don't say anything today. Why? Sorry, I say that this is... No, the word is not complicated, it's weird. Vector calculus weird. Okay, so we start review. We continue on Friday. We start. Question one, the review. Review for test number 4, vector calculus. Question 1. Say compute this integral. Line integral. X dy plus y dx. And who is z? Well, z is a curve. It's a curve. Okay, give me a favor to parametrization. Okay, I appreciate it so much. Entonces, the vector value function depending on only one variable que es t, y es 2t, 3t, no? And t, the domain of t is important. When you remember, when you parametrization, if you don't specification the domain, you are doing nothing. Okay, cool. So now I copy here in one corner of the piece of paper. I copy. Okay, this is x and this is y in the parametrization. So x is 2t and y is 3t. Therefore, dx is the derivative de this que es 2 dt. And dy is the derivative de this que es 3 dt. Boom, ready to plug in here. You convert magically this line integral in one single integral of the calculus 1 from 0 to 1, que es the domain of t. And you copy x. Who is x? 2t. Who is dy? 3t. 3 dt. Sorry. Plus, who is y? Y is 3t. Who is dx? Is 2t. 2 dt. Sorry. But actually, this is 6t and 6t. No? It's 12t. 12t dt, no? Entonces, the integration of piece okay is 12t squared over 2, evaluating between 0 and 1. Well, this is actually 6t squared, no? Evaluating between 0 and 1. It's obviously 6 the answer. Because 0 is 0. Easy or no? This is the kind of question. It's okay. Now, it's important. Friday is the most important day. Okay, Friday, we are doing the review, the majority of the review. Friday and Monday next week. And that's it, because my plan is maybe Friday I send the test and you start working. Remember the due date for this test is July 28. Let's do everything, guys. I close 29 in the morning. So you forgot to send me something, sorry, 0 for you. So now we spend the time Friday, and Monday, to complete the review. We have class Wednesday, yes. This is extra. No mandatory attendance. I want to discuss in one topic I consider fantastic to clarify everything in vector calculus. Okay? Do you follow me? Are you clear?
Yes, clear.
Okay. So now, have a nice day. I am leaving now.
Have a nice day, Professor. See you Friday.
Okay.